Hi, everyone. My name's Arthur. I'm an assistant professor at Georgia Tech in the Stewart School of Industrial and Systems Engineering. And today I'm going to talk to you about our paper presented at EC in 2023 called Reducing Marketplace Interference Bias via Shadow Prices. And this is joint work with Ilan Lobel from NYU and Ido Bright from Lyft. So what we're going to talk about today is experimentation, and experimentation in marketplaces. As many of you probably know, we've had lots of new digital marketplaces pop up over the last 10 years. And one of the key ways in which these marketplaces tend to operate is they like to experiment. They like to try things out, see if it improves the metrics they care about, and then ship or not ship these features based on the results of those experiments. So all sorts of companies run these experiments all the time, and we have lots of interest in A/B testing as a result. But it turns out that running experiments in digital marketplaces has some challenges. And one of those challenges is called interference. So let me try to introduce that problem. So in a traditional randomized controlled trial, which I'll call an RCT for short, the way that it typically works is we're going to randomly assign units to control here in blue or treatment in green. Then we'll kind of look at the outcome of these different units. And then we will compare the average outcome in the control group and the average outcome in the treatment group. And that'll tell us whether the treatment is a good idea or not. And the thing is, this type of experiment, you've been using these types of experiments for over 100 years, especially for things like developing drugs. And the thing is that in order for this type of experiment to work, it relies on a very strong assumption, which is that the outcome of a particular unit only depends on the treatment assignment of that unit. So if somebody else is assigned to control a treatment, it shouldn't affect how the outcome that I have. And the thing is, in marketplaces, this assumption, which is called SUTVA for stable unit treatment value assumption, it might not hold, because if I intervene on one unit, that can affect the outcome of another unit. And this is called interference. You have a unit interfering with another unit. And this creates bias when we try to estimate results from an experiment. So how do we reduce this problem, right? We're not the first ones to think about this problem. And there's really two schools of thought on how we can reduce interference bias. The first one is that, well, we should design smarter experiments. Lots of literature here, lots of smart designs. So you can basically you change the unit of randomization so that you're less likely to have interference between two different units. And then the second school of thought is around new estimators. And this, I would say, is a little bit less active of an area, or there's been a little bit less work here. And our work falls under this category. And the key idea behind our work is we're going to try to figure out how interference can actually be directly captured by the way the marketplace is structured. And a key insight in our work is that not all marketplaces are the same. We're going to differentiate between marketplaces where users have a bunch of choice, right? So for example, when you think about Amazon, Airbnb, once a user has been presented with a set of options, the user can decide what to do. And we're going to differentiate this type of marketplace with what we call a matching-based marketplace, where a user will request a service, like a ride, and then they will be assigned by the platform to a unit of supply that sort of selected by the platform with some global system value in mind. And we are going to focus primarily on these matching-based marketplaces today. So let me give you an example of interference bias arising in a matching-based marketplace. So here we've got a ride-hailing example. We've got some customers. They're going to book half the time on average. So, if we don't have any sort of treatment, we might have an outcome where two people make a request, 2 out of 4, and then the platform matches them to vehicles according to some criteria like, distance, pickup distance, and things like that. Now let's imagine that we have a treatment, and our treatment is really effective. Our treatment makes customers book 100% of the time, okay? So now we're going to run an experiment. We're going to put half of our users in treatment and the other half in control. So what happens? Now we're going to get 3 requests. And as a result, we are going to, the platform is going to match those requests to drivers. And what you'll notice is that the third person here is now matched to a different vehicle in the experimental state than they would have been matched to in the global control state. And so that means that we have new treatment requests changing the outcome for the control group. And this is a textbook example of interference. So let's, in order to kind of model this, we want to work on kind of a really, really simple matching marketplace. Like, what does a matching marketplace look like? So in our model, we're going to have some demand types, a finite number, ND. And we're going to say that there's going to be a Poisson process that determines the number of arrivals of each type. And we're going to have, on the other side of the marketplace, some different types of supply. And they're going to, their arrivals are also going to be Poisson distributed. And we're going to assume that we have a value of matching demand type I to supply type J. And we're going to denote that value by V. And then what the platform is trying to do, given a realized demand from the Poisson demand process D, and a realized supply from the Poisson supply process S, the platform is going to try to maximize total value. Okay, so you've probably seen this type of formulation before. This is kind of a standard transportation or bipartite matching problem. And importantly, this is a linear program. This is a linear program, even though the outcome is kind of a discrete choice, right? We're not going to match, we're not going to have fractional matches. We can't split riders between multiple cars. But it turns out that we don't need to consider the discreteness. This is a problem that can be solved as a linear program. And what that means is that it can equivalently be formulated using the dual of this linear program. And I don't want to talk too much about this dual. I mean, again, you've probably seen this in a textbook at some point. But what I do want to highlight is the decision variables of the platform. So in the primal formulation, the decision variables are these xij's that match, that kind of say how many units of type I, of demand units of type I, are matched to supply units of type J. And in the dual, the decision variables are sort of marginal values or shadow prices of each type of demand and each type of supply. And so these shadow prices or dual variables, they capture, interesting, they capture the interesting properties of the structure of the marketplace and the structure of the optimal solution. Okay, so what does our experimental setting look like, right? We're trying to debias experimental estimators. So we're going to assume that our experimental setting is entirely demand side. And this is just for, without loss of generality, you could do this on the supply side as well. So we're going to assume that under control, our demand types each arrive at rate lambda I. And treatment is going to give us a boost in demand arrival rate. So under treatment, the arrival rate is lambda plus beta. So what we're interested in comparing is what is the expected system value when under the control arrival rates versus what is the expected system value under the treatment arrival rates. And this estimate we are going to call the global treatment effect. So it's the value, it's the difference in values between everybody being in control or everybody being in treatment. Now, of course, we can't observe both of these states simultaneously. We can't, we can't duplicate the world. So, but what we can do is we can run an experiment. And in the experiment, we're going to split up units. We're going to have some of them in control, some of them in treatment. And as a result, we'll kind of observe a hybrid state, which we'll call the experimental state, where the arrival rate of demand is going to be 1 minus rho lambda plus rho times lambda plus beta. So lambda plus rho times beta. And we're going to use data from this experimental state, from solving this experimental state, to build an estimator. Okay, so what is the standard estimator, right? So far, this is kind of a normal setup. What's the standard way to solve this estimation problem? Well, the standard way is we're going to look at how many units of demand units of type I were matched to supply units of type J in the treatment group and in the control group. And we'll look at how much value we got from all the treatment users and how much value we got from all the control users. And we'll take the difference, appropriately scaled, to take into account the relative size of the treatment group and the control group, right? So this is just the difference, total value that we get from the control group, total value that we get from the treatment group in the experiment, scale those up, take the difference. So just in the interest of time, let me skip this example because I think this is kind of a, it's a very straightforward estimator. Now, in order to analyze the performance of this estimator, we're going to make a simplification of our model, which is that, to kind of avoid like small sample size type effects, we're going to work in a limit where we kind of have a lot of demand and a lot of supply. The market is sort of thick. And in that case, we call this the fluid limit. So in this case, what happens? Well, in this case, what happens is that the value function, the value of the matching problem, instead of being an expectation over these sort of arrival processes for supply and demand, just become a deterministic linear program, where instead of putting the realizations from the Poisson processes, we put the Poisson rates. So then in this fluid limit, what happens to the global treatment effect? Well, the global treatment effect is still the difference between the expected value of the expected system value under global treatment minus the expected system value under global control. But now those two terms are deterministic linear programs. And the nice thing about that, this simplification, analyzing the system in this regime, is that it will allow us to really expose why the standard RCT estimator suffers from interference bias and therefore propose good solutions. So what does the RCT estimator do? What is it actually doing in the fluid limit? And it turns out that what the RCT estimator is doing, the standard estimator, is it's actually, by summing up all the value in the treatment group, summing up all the value in the control group, scaling up and taking the difference, what it's actually doing implicitly is it's taking the average value from each type and looking at the difference in arrival rates for that type and saying, the product of those two things is going to be my treatment effect. So, intuitively, this might not be such a bad idea. And actually, in the absence of sort of these marketplace dynamics and the absence of kind of demand and supply competing for each other, this works perfectly well. But as we'll show, when you start having competition as often arises in a marketplace, then this might not work so well. And why is the case? Why is that the case? Let's look at a simple example. Okay, so simple example, we have one type of demand. We have 6 types of supply. And just to, to magnify this, we're going to assume that the treatment effect on demand here is huge. So arrival rate is 1.5 under global control, 5.5 under global treatment. And then each of the supply types has an arrival rate of 1. And we've sort of ordered the types in terms of like which type is most valuable to our demand type. So the first type Every time we can get a match, we get value 2. The second type, we get value 1, and so on, dividing by 2 each time. So what does our matching value function look like in this toy example? Right? So let's plot the value function as a function of the demand arrival rate. So over here on the left, we are in global control. And over here on the right, we are in global treatment with arrival rates lambda1 and lambda1 plus beta, respectively. And what you see is that the value function is going to be piecewise linear and concave in lambda. As lambda is really small, we get to match always with our best type, best supply type, type 1, which gives us a value of 2. And therefore, the slope of this piece here is 2. And then at some point, we run out of supply type 1, and we need to match the supply type 2. And now, instead of getting a value of 2 for each match, we get a value of 1. And then eventually we run out of supply type 2. And every time we run out of a supply type, we hit a breakpoint in this curve, and the slope gets smaller. And so what we're trying to estimate is the difference in the value function at global control with the value function at global treatment up here, global control down here, and we wanted to take the difference. So what does the RCT estimator do? How does it do this? Well, remember what it does is it takes the average value computed at this experiment state, which is in the middle, at the midpoint between the global control and the global treatment space. And it says, however much average value I'm getting now, if I get more demand, as I will in the global treatment state, the total system value will grow proportionally with the demand, and the proportionality constant is going to be the average value of each type. So what does that mean kind of graphically? It means that we are building a linear approximation of the system value function implicitly. And that linear approximation interpolates between the value of the experiment state and the value at 0. Now, and so as a result, what the RCT estimator then takes, it says, well, the estimated value of global treatment is given by our linear approximation here. The estimated value at global control is given by our linear approximation there. And the difference is our estimator of our treatment effect. And you can see, right, you don't need to be an expert in taking linear approximations of functions to know that this is probably not the best way to approximate the value function. So, and what we can actually show is that because this is what the RCT estimator is doing implicitly under the hood, it's doing this weird interpolation approximation technique. As a result, this standard estimator is going to be biased. It's always going to overestimate the treatment effect in amplitude. And you notice here I have to add an assumption which says that the treatment effect across all types is, I either increase the arrival rates across all types or I decrease the arrival rates across all types. And you might think, wow, this seems like a pretty strong assumption, but actually you really need it because if you have some arrival rates that are increasing and some that are decreasing, then the RCT estimator can kind of get lucky and overestimate one effect in amplitude and the other effect in amplitude, but they have opposite signs, so they kind of cancel. And obviously, that's not a really satisfying, that's not a really satisfying outcome. We don't want our estimator to be unbiased just out of luck, but it can happen. Okay, so we have this RCT estimator. It's biased, and it's biased because under the hood, it relies on this very sort of rough linear approximation of a piecewise linear concave function. So the question is, how do we replace this estimator with something that's not going to suffer from this, underlying misapproximation? Well, if we take a look at the RCT estimator, we see, right, we've got two terms. We've got the value in treatment. We've got the value in control. And what we said is, actually, when it comes down to it, really, we're really saying, look at the average value from each type and then count up how many units we have in the treatment and how many units we have in control. And all I'm writing here, all I'm saying is that the sum of a bunch of numbers is equal to the average of those numbers times the number of numbers. That's really all I'm saying. But now what we can do is we can say, well, actually, this average here, this is what's leading to the weird approximation, the weird linear approximation. So what if instead of looking at the average value, we look at the marginal value as captured by the dual variables, by the shadow prices of the linear program? And you can probably guess where this is going, right? Because I talked about linear approximation, and I talked about, bad linear approximations. So in the fluid limit, what does this end up looking like? It looks remarkably similar to our RCT estimator, where we have something that's linear in beta, linear in the demand arrival rate increase. But now the slope is not given by the average value, it's given by the marginal value. And graphically, what does that mean? It means that we are still building an implicit linear approximation of our value function. But that implicit linear approximation is now the sort of Taylor first-order approximation. And in a way, that's kind of the best first-order approximation you can do, especially for a function that's locally linear. And you can tell, by the way, that this isn't guaranteed to remove all bias, right? But it's certainly a lot closer to what the global treatment effect is supposed to look like. And indeed, we can show, so we need to keep our sort of sign consistency assumption that says that the effect is either positive on all types or negative on all types. And we also need to add an additional assumption which says that the experiment, the size of the control group and treatment group is the same. But when you make those two assumptions, we can show that we provably reduce bias in the fluid limit. And this symmetric assumption, I acknowledge, is pretty strong. And it turns out that actually we can relax this. If you just want to have provable bias reduction, you can kind of take a convex combination of the shadow price and the RCT estimator. And that kind of removes the pathological edge cases, which can happen when the experiment is not symmetric. So that's kind of a way to fix that, and that's a way that you can get sort of provable bias reduction for any fraction of your population that's going to be exposed to treatment. And we have some additional results. For one first result, which I think is quite cute, though not necessarily the most practical. If you actually select the treatment fraction at random, it turns out that the shadow price estimator is unbiased. And this is true in the fluid limit, and it's true in the finite sample setting. It's kind of a cool result. It relies on basically the fundamental theorem of calculus, which turns out is actually really useful even many years after you leave high school. And we also have some results that show that actually not only do we reduce bias, but in terms of variance, we're also better off using the shadow price estimator. And really, this variance reduction comes from the fact that shadow prices marginal values tend to be smaller than average values. And so, if there's noise, at least you're multiplying by a smaller number. And so you're not amplifying the noise as much. So here's some numerical experiments. We have a simulation where we have this is like a simulated ride-hailing setting using New York City taxi data. So I have a fixed number of drivers. And then on the x-axis, I'm going to vary the number of passengers that are making requests. So on the left, I have a very small number of passengers relative to the number of drivers. So that means I'm not going to have, they're not really competing for drivers. But then on the right, I'm going to have a large number of passengers that are competing for the drivers. And the three different groups of curves in three different colors are going to show three different increases in the demand arrival rates, 10%, 5%, 3%. And then the curves show the effect of that increase in demand arrival rate on the total system value. So the solid curve is the actual increase. And you see that it's kind of decreasing as we move from left to right, because as passengers start competing for drivers, having 10% extra requests isn't actually going to give you 10% extra value. It's going to give you less than that because there's competition. And what you can see is that the diamonds, the shadow price estimator, really track that actual effect quite well. They really capture that contention for supply. Whereas the RCT estimator, the standard estimator, doesn't capture that at all. And it kind of says, well, you know what? The average, on average, we get an increase in system value that's just proportional to the demand arrival rate increase. So just some quick takeaways. I think there is a lot of work in the literature that says that actually modeling interference directly can be really difficult. And I think one of the reasons for that is because a lot of the work focuses on these choice-based marketplaces where there's users making decisions. That's a very hard process to model. That's a very hard process to capture. So it's really not very surprising that this is a very, modeling the interference between these super random user behaviors is very difficult. But it turns out that in matching marketplaces, because the platform has so much decision power over the outcomes of each demand and supply unit, it turns out that we can use this decision power to really capture the structure of interference and use that to design better, less biased estimators. And I guess my other takeaway is that, linear programming 101 is super useful, and we should all be paying attention in our first year PhD courses. So thanks very much, and I hope you enjoyed the talk.